Okay. With that, we'll go ahead and move on to our pressure, because we keep talking about this pressure. Pressure is that force of our gas particles. Okay, well, interestingly enough, there is gas around us all the time. So there's always an external force. Okay, that force is what's helping to keep our individual shapes. It's what's keeping liquids as liquids. Okay, so all of those forces can be felt, even though we can't see them. Okay, and this is where we end up coming up with a way to quantify this pressure. And what we've got here is what's known as a barometer. And what barometers do is monitor that pressure or measure it. Okay, and how do we measure it? We have to make it visual. So to do that, what we're going to do is take a tube that is open at one end, and we're going to fill it with a liquid. Okay, in this case, that liquid is mercury, but let's just fill it with a liquid. We'll then invert that tube in a bath of that same liquid. Okay, and so what we would expect, because if we just inverted that tube, the liquid should fall out of said tube. But if I've now inverted it into a secondary container that has more liquid in the bottom of it, we'll notice the liquid doesn't all just fall out. And you can do this at home if you like. If you've got a glass, okay, and then a large pot, fill the pot maybe halfway with water, then fill your glass with water, and very quickly invert it carefully, don't break your glass, into the pot of water. And you'll notice that the water in the glass will actually stay above the level in the pot. And the reason for that is an external pressure. There's an external pressure from the gas pushing down on the liquid in the pot. Because it's pushing down on the liquid, this liquid, also trying to push down, now has something pushing against it, because the liquid in the pot is now going to be pushing up on that liquid in there, preventing it from coming out. Okay, so what we could go through and do on our barometer then is just look and kind of say, well, oh, the liquid stayed up that high. It didn't fall all the way down. Okay, that in and of itself is just a neat parlor trick until we notice weather patterns. And when the weather changes, that level goes up or down depending on weather. And this is where we have meteorology as a field of science, because what we're doing is studying how different weather patterns affect pressure and vice versa. So because we notice it changes, if we can quantify that, we could then potentially use this parlor trick and be like, tomorrow it is going to rain, and everybody laughs at you until tomorrow it rains, and then you go, oh my God, you must have known magic. Well, no, we just knew how to make observations about pressure differences and tied those pressure differences to weather patterns. So that's kind of neat, right? And that's what's happening. Because of that, though, you have to be able to quantify that difference, because maybe just a small change in pressure doesn't actually mean rain. Maybe you actually need a really large change in pressure to differentiate for rain. So that means we need to have those individual markings graduated out. Okay? How are we measuring that distance then? Well, that distance then goes to inches or centimeters, okay, or millimeters. And we'll just measure the height of our tube. We need a standard method for this. The liquid that is typically put into our barometers is mercury, and we'll look at why we pick mercury here in a second. Okay, and we just reference the height of liquid in that tube. If the height is at 29.9 inches of mercury, well, we just say we're at normal atmospheric pressure. Okay, what happens if it goes up or down? Well, that's going to help us to predict different weather patterns. Okay, so now let's move to the next aspect. Why mercury? Well, what if it wasn't mercury? Okay, that's usually the best bet. Okay, why one thing? We'll change it to something else. Let's make it water. If I had just a container of water, so now let's be less fancy, just a container of water, and we left it out on the counter, what happens to the level of water? Okay, well, it goes down because your brother came along and drank it. Keep your brother out of this, okay, or your sister, or your parent, or your dad, or you, the dog, okay? Just take that container of water, leave it on the counter, okay? And come back to it every couple days. And what you'll notice is that that water volume will drop. And eventually, it will all disappear. Okay, well, why is that? What's happening is the water is transitioning into a gas. It's transitioning at a very small extent, which is why we can see it there for a while. If we'd done that with a beaker of gas, our house would probably burn down. Okay, but if we'd used gasoline, that wouldn't have lasted there very long. That we probably would have noticeably seen that level go down across the course of hours, as opposed to the water, which might be days. Okay, so there's a different property of those individual liquids. That property becomes important because when we're looking at our barometer, we need to make sure that this level of liquid at the bottom is constantly pushing up on that tube with the same force. If that level drops because the liquid is becoming a gas out here, well, now the upward force changes. If the upward force changes, the level in the tube now has some flux and change to it. It's changing not because of weather patterns, it's changing because our liquid is disappearing. Okay? And that becomes an issue. So why mercury? Well, mercury stays a liquid. It doesn't change into the gas easily. Water, on the other hand, will change to the gas very, very quickly. So we now have an observation of this. We need to, of course, come up with a name for it, and this is vapor pressure. So vapor pressure is the pressure of a gas. It's pressure, so it has to be a gas, but it's coming from a liquid. So if I just have a liquid chilling, the pressure of the gas above it that came from the liquid is known as the vapor pressure. So if I have a really big vapor pressure, that means that liquid is transitioning to the gas to a large extent. Okay? As we change temperature, would we expect the vapor pressure to change? Well, 1 degree water is almost a solid. 99 degree water is almost a gas. Would I expect the amount of gas at 99 degrees to be different than the amount of gas at 1 degree? Yes. So vapor pressure has a strong temperature dependence. Okay? As we increase temperature, our vapor pressure will drastically increase as well. Okay? And so what we would just do is report the pressure of the gas coming from a liquid as our vapor pressure at an individual temperature. And so when we're talking about trying to measure weather patterns and get atmospheric pressure, we want vapor pressures of liquids to be insanely small. Okay, why do they need to be small? Well, remember, the whole point of this was that the liquid stays a liquid. Okay, it does not transition to the gas. Vapor pressure is by definition the gas. So I want a small amount of gas present, okay, for my barometry experiment or my weather pattern experiments. Okay. As a slight side note, which we will discuss later in the semester, what about dissolving gases into liquids? Okay, so this isn't really vapor pressure, okay, but we've looked at something kind of similar to this, and it's a similar concept. What happens if we dissolve solids into liquids? Okay, and in particular, what we're referencing is with temperature. What happens if I increase the temperature to the amount of solid dissolving? Okay, the solid dissolving goes up. Okay, I get more solid to dissolve at higher temperatures. What about with gases? What happens if I increase the temperature with a gas? Does the dissolving go up or down? Well, it should go up because the other one went up. It actually goes down. Okay? And this on the surface may seem contradictory, but let's think about this a little bit differently. We've got a solid transitioning to a liquid, which can transition to a gas. To go from a solid to a liquid, we are increasing temperature, right? Okay? So if I'm looking at the dissolving process, I'm taking a solid and trying to make it a liquid, I need to increase temperature. That's how we transition from solids to liquids. When I'm looking about dissolving a gas, I'm taking a gas and trying to turn it into a liquid. Well, to go from gas to liquid, I don't add heat, I remove heat. That's why the temperature needs to decrease. This is why we're seeing an apparent contradiction. It's not a contradiction if we understand how we transition between our phases with melting points and boiling points and all of that fun jazz. So that's kind of neat. Okay? That, interestingly enough, is test questions. So you should note that and remember that. Might be a good thing to add to the shared slides or shared notes. Okay? So now that we have a pressure, we need to quantify it. We already addressed some of that quantification. We can do millimeters of mercury, so measure a length of the mercury in our tube. Depending on who we talk to, because this is such a big observation and where we're making that observation, the units of pressure go absolutely bonkers. Okay, so there are tons of units for pressures, which would theoretically mean you would need to convert them all. I'm just going to blanket statement say, don't worry about it. Okay, when it comes to pressure, I really only want you to deal with atmosphere as a unit, and the reason I want you to deal with atmospheres is the number associated with that pressure unit is 1. Whereas if we look at any of the other pressure units, the standard pressure is some weird, goofy number that isn't easy to memorize. Okay? If you have to move into 151, or perhaps even into engineering, you will likely be responsible for doing these conversions. You should be able to do them because you know dimensional analysis. Okay? But for this class, you don't have to stress about it. All I really want you to know is 1 atmosphere. Okay. So now we've got all of these things. We've got pressure, we've got temperature, we addressed volume. Okay? One thing we haven't addressed yet is the amount of particles. Okay? But we'll look at that here in just a second.